In this section, we'll be looking at conditional probability mass functions and conditional expectation as well. So this is looking at how do we take a PMF or a random variable that we already know and condition it? How do we apply a conditioning? And we're going to look at this next slide, and just fair warning, there's a lot of equations, but ultimately we're going to draw a correlation between a unconditional probability mass function or an unconditional random variable and show the equivalent equation for a conditioned random variable or a conditioned PMF. And so there's going to be a lot of equations, but just know that they are all pretty much the same equation, but with conditioning. So the first equation that we can look at here is in the top left, and this is that the probability mass function of a given random variable x for a specific x, little x that is we can write it as the probability that our random variable is equal to the specific value little x. And if we translate that into conditional probabilities, the only thing that we really care about conditioning here is the little x, right? We don't need to condition the variable itself, right? It is a variable. It's not an actual value. And so what we could write this as is the PMF of x given a, or of x conditioned on a. So again, we're conditioning our random variable on an event a for a specific value of x is just equal to the probability that our random variable is equal to a specific value given that a has occurred, right? This is saying the value, so maybe a 1 or a 4, but the probability that x is equal to x is equal to little x given a. Now the next equation is that the sum over all possible values of the random variable of a PMF must be equal to 1, basically saying the probability of all possible outcomes of a random variable has to be equal to 1. And so the exact same applies over here with conditioning. We would say that the sum over all possible values of x of the PMF, the probability mass function, of the random variable x given a for all values of little x must be equal to 1. So even when we condition, just like a regular conditional probability, our sample space, our omega, if you will, for the probability mass function must equal 1. The next equation is the expected value of x, and we said earlier that that is equal to the sum over all possible values of the random variable x of the value multiplied by the probability of that value, the PMF of that value, more accurately stated. And so we can, again, draw a correlation over to our conditional version of this, which is saying the expected value of a random variable x, given that an event A has occurred, is equal to the sum over all possible values of our random variable x of the value of the random variable multiplied by the probability of that random variable given A. So again, we're taking this section of the equation, which we've said is really just pulling from this formula up here, right? We're just saying that it's the probability that the random variable is equal to x given that A has occurred, or that the random variable is equal to a specific value given that A has occurred. And then the last equation that we'll look at here is the expected value of a function of x, of some g of x, a function of a random variable. And we said earlier that that is equal to the sum over all possible values of the random variable of the function of x multiplied by the PMF at that specific value of x. So again, this is the function of the specific value, this function applied to the specific value, multiplied by the PMF of that specific value. And we can write the same thing for the expected value of a function given that an event A has occurred. And we would say, again, the value of our PMF doesn't change. G of x is still the same. But now we write again that we condition the probability, the PMF of x given A, and again, we pull that out of our first equation here. So all of those equations are a lot to look at, but let's go ahead and apply them to a specific example. So let's assume that we have a uniformly distributed PMF, specifically with a random variable x. So the first thing that we may want to do is calculate the expected value of that random variable, and we'll go ahead and calculate the variance of that variable as well. So if this right here is our specific PMF, so this is a uniformly distributed PMF, values ranging from 1 to 4, we can go through and calculate that the expected value of x is really just the midpoint. And so the midpoint here for a uniformly distributed function is going to be right in the middle here at 2.5. So we can just look at that one and say what it is because it's uniformly distributed. So E of x is equal to 2.5. Now the variance of x gets a little bit more interesting, but as you may recall from the earlier lecture about the variance of the uniform distribution, we said that the variance of a uniformly distributed random variable x is just equal to 1/12 of b minus a multiplied by b minus a plus 2. And in this case, we know that b is equal to 4 and that a is equal to 1. Now, through that, we can go through and plug in those values. Well, b minus a is just 4 minus 1, or 3, and b minus a plus 2 is 5. So we can write that this is 1/12 multiplied by 3 multiplied by 5, which is equal to 5/4, or 1 1/4. Now, to do this in a slightly different way, let's say that we have an event A that is that x is greater than or equal to 2. So with that event, what is the new expected value, the expected value of x conditioned on A, and what's the new variance of x conditioned on A? Well, again, the expected value is relatively easy to calculate. We can say that the expected value of x given A in this specific case is just the mean here because it's uniformly distributed, and that's going to be 3. So the expected value here is 3. You'll notice that's shifted up because 1 is not greater than or equal to 2. So this is a 0 probability here. Now, one of the things that's important to look at, because we're going to calculate the variance, is what is the probability of each specific value. This is uniformly distributed. There are now 3 different values. Previously, each value had probability 1/4 of occurring. Now each value has probability 1/3 of occurring because there are 3 values, and again, this is uniformly distributed. So if we wanted to calculate the variance of x given A, we would write the variance of the random variable x given that the event A has occurred. We can write this using our base notation, which is that this is equal to the expected value of the equation x minus mu, our mean, squared. And when we plug in some numbers to this, we'll find that this is 1/3 the probability of x minus mu squared. X will start with 4 and say that this is 4 minus 3 quantity squared plus 1/3. And we'll look at our next value, 3. So 3 minus 3 squared. And then finally 1/3 the probability of this last event, and we'll say that that is 2 minus 3 squared. So solving this, we find that this is 1/3 times 1 squared for this first term, 1/3 times 0 squared, and 1/3 times minus 1 squared, which at the end of the day is 2 1/3s multiplied by a 1, or just 2 thirds. So the variance in this case is 2 thirds. Now, if we go back and look at our first example, it was 5/4, which makes sense if you think about this conceptually. So in the top example, we have a variance that is broader. We have a broader spread from the mean than we do in the bottom example. In the bottom example, we have, if you will, cut off the value of 1. So we now only have a variance from 2 to 4. You'll also notice that our mean has shifted up from 2.5 to 3, as would make sense in this scenario as well.